All right, so hi, I'm Ionatan. I'm a PhD student with WagMod NYU. And today I'm going to be talking about some work we've been doing on decision-making in large-scale data. So I wanted to start by sort of framing this talk with the relationship between task performance and task engagement, which I think is a pretty natural one to think about. So I'll start with a real-world example that maybe hits a little bit too close to home. But for example, maybe some of us have thought about dropping out of grad school. And the more we engage in the task of being in grad school by going to classes or listening to talks, we sharpen our research skills. But then maybe getting rejected from a journal or a grant can cause us to want to quit and drop out, while maybe something on a more positive note, like an acceptance, can have the opposite effect. And so in reality, the directionality of this relationship between task performance and task engagement is hard to pin down. Like, do people drop out because of changes in performance? Or alternatively, do people who are about to quit lose motivation, try less hard, and therefore exhibit a drop in performance? What about the contribution of external factors, the contribution of learning rates and internal motivation? So it's a really complex relationship that is maybe seemingly simple at first glance. So to start talking about this, I wanted to talk a little bit about the theoretical and empirical basis for this relationship. And to do that, we have to look at two sets of literature, which are on skill acquisition and intrinsic motivation. And hopefully this is also going to serve to show how disentangling the relationship between learning and dropout, which I'm going to use a little bit interchangeably throughout the talk with task performance and task engagement, is more challenging than it might seem, and why we really need models to be able to do so. So in terms of skill acquisition, early work on skill acquisition comes from modeling efforts looking at simple descriptive rules for learning as a function of practice. So these are like exponential and power laws. In recent years, however, there have been more nuanced views of learning that have emerged that have emphasized things like practice, grit, and perseverance as ways to improve performance. Note that these are already somehow related to intrinsic motivation. And finally, self-regulated learning is an active area of applied and theoretical research, where when and how learning takes place is important, but not always considered. On intrinsic motivation, there's also conflicting evidence. So on one hand, we know that moderate challenges encourage people to continue with a specific task, while extremely easy or extremely difficult tasks cause people to lose motivation. Meanwhile, other work has found that peak and end experiences change users' perception of a task, which also may be linked with motivation. And finally, there's work on gameplay, which kind of lies somewhere in the middle, stating that setting that rewards and other factors impact motivation to continue with the task, while peak and end effects can impact people's assessment of game difficulty and fun, and maybe not necessarily performance. So all of this is to show that literature here is complicated in terms of the relationship between learning and dropout. So to fully account for such data, we really need joint accounts of learning and dropout. And recently, a number of modeling approaches have started to do this, and our work here kind of fits in with that line of research. So a few papers have started to pinpoint the relationship between performance and quitting using established models, such as epsilon machines, which you see on the right here, to describe the optimal transitions between states, or geometric models to describe quitting distributions. Meanwhile, there have been other papers that look at how learning functions change, specifically based on dropout and age and other related factors. However, these are really starting points for describing the complex dependency that I outlined earlier. And like I mentioned before, we really need rich data sets and models that help us gain an understanding of how this works. Okay, so if we want to study learning and dropout in tandem, what kind of data sets should we use? And I'd like to argue that large-scale data sets have become a lot more common in cognitive science over the past few years and are perfect for sort of addressing this problem. And there are a lot of good reasons why these have gained traction in cognitive science over the past few years. So one is to obtain rich data in participants' real-world environments. Another is to study a wide range of cognitive mechanisms, or to even use machine learning methods, which need a lot of data. So once you collect a data set like this, you can really ask a bunch of interesting questions. And then also to investigate if results or models derived from constrained lab settings generalize to more naturalistic settings. And here are just a few examples of recent big data studies in cognitive science. which look at how uncertainty drives exploration or how cognitive abilities change with different demographics, or use machine learning to improve cognitive modeling. So hopefully this highlights a little bit of the different approaches that you can take if you have such a data set. Okay, so what task and data set do we actually use in our lab? So we study planning, and to do so, we use this task called 4 in a row, which is a 2-player combinatorial game where players alternate placing pieces on a 4x9 board, trying to connect 4 in any orientation. So here I'm going to show you a demonstration of a game between 2 humans that we collected in the lab. And just by this sort of simple demonstration of one game, I hope you can already pick up that while the rules of the game are simple and kind of intuitive, there is a decent amount of complexity and nuance in the task. So here, for example, you'll see in a second that black only wins because they create this double threat that white can't defend against by connecting the 4 in a row there. So I'm going to touch a little bit on this task and some of our previous work on it throughout this talk. But if you're curious about some of our modeling efforts on planning or any of the in-lab experiments that we ran and those kind of analyses, the preprint for that is right there. Okay, so how did we actually take this task and then scale it up to this massive data set that I outlined at the beginning? So to do so, we partnered with Peak, which is this mobile app company that put the game on their platform, and then they send us back anonymized data. So here's how the gamified version of 4 in a row looks on their platform compared to the in-lab version that we ran earlier. And some features of this data set. So these are all human versus AI games. The AIs use a version of our planning model, which is in the preprint that I just mentioned. And currently we have about 10.8 million games from 1.2 million unique users, and this data set's actually still growing. So at some point, I'm not going to know what to do with that amount of data anymore. And to really sort of drive home how large this data set is, here's a histogram of the number of games played by all users. And so you can see that many users play just a few games, like even less than 5. But if we blow up the tail of this plot, we see that there are thousands of users who played even up to 100 or more games. So this data set, I would argue, lends itself really well to studying learning and dropout for a variety of reasons. But because people play on their phones at will, they have complete autonomy over when they can stop engaging with the task and drop out. And so that's sort of perfect for what we want to do with learning and dropout. Okay, so to start looking at task performance and task engagement, we wanted to first characterize the endpoint of these two processes. To quantify human performance in this task, we use playing strength, and for that we use ELA ratings, which are a measure of playing strength that we borrow from chess. ELA ratings are relative, so that sort of means that if you have, let's say, a score of 200 higher in terms of ELA rating than me, if we were to play each other, then you have about a 76% win rate against me. And we compute ELA ratings in 20-game blocks based on user results against the AI to get reliable estimates so that we have a reasonable number of games to compute values over. So first, we see that ELA ratings are diverse. So this is just a histogram of people's final ELA ratings in the last block, so the last 20 games of gameplay, and users score across a pretty wide range. Next, we wanted to look at the relationship between final playing strength and total number of games played, since this gives us a nice measure of both final performance and engagement for every user in the data set that had played at least 20 games. And we see that these are correlated, but this gives us no real insight into how people get to this point. So to understand how this happens, we like to think about the relationship between learning and dropout, which I'm going to try to explain didactically. So we start with the idea that two factors might be at play here, which are each individual's learning rates, so how they improve, and how task performance leads to dropout. So if we take as an example, as an extreme example, a user in the bottom left, this would be someone who doesn't learn a lot per trial, so their playing strength stays pretty constant across gameplay, and is unlikely to drop out with higher scores. So in other words, initial abilities matter a lot for their dropout behavior. On the other end, we can imagine another extreme user who learns a lot per trial and is more likely to drop out with higher scores. So this would mean that change in performance over time is much more important for dropout behavior. And of course, these are just extreme examples, and people might lie anywhere on sort of the subspace between these two data points. So for the rest of the talk, I'm going to dive into what analyses we can do to see where on this spectrum people behave in our task and in our data set. So we started by looking at the factors driving dropout behavior and hypothesized that this was driven by current playing strength and current experience levels. So note that these are current rather than final values like I showed a few slides ago. So we're really trying to monitor progress rather than the endpoint. And to look at this, we did a logistic regression on how these values in a given block of 20 games influence the probability that users will stop participating in the next block of 20 games. And this led to two results, which are that stopping probability decreases as users play more games. So this is going towards the right on that heat map. And also that stopping probability increases with higher ELO ratings. So that's going up on the heat map. So this gives a slightly counterintuitive result that stronger players are more likely to stop. But it does link with the motivation literature that I cited earlier on lack of a challenge or lack of information game leading to dropout. Conversely, we didn't find any evidence that the task was too difficult, and that in turn leads to dropout. This might be due to our AI agent strengths and the way they're coded up on the Peak platform. It's definitely something we want to keep looking into. Okay, before we get to improvement and learning, we wanted to also investigate at least a first pass at this peak end effect that I mentioned in the introduction. And so to do that, we analyzed streaks of behavior right before dropout. So this is counting the number of users who had consecutive losses before quitting, which are negative X values on the plot here, or consecutive wins before quitting, which are positive X values on the plot here. And you'd imagine that any end effects, at least, would lead to a sort of bimodal distribution where many users have streaks of either a lot of losses or a lot of wins right before they quit. And in fact, we didn't find any evidence of that. So this is pretty evenly distributed, maybe a slight lenience towards a few wins before dropout. Okay, so to investigate learning and show that users' playing strength increases over time, we first did the simplest thing, which is just to look at individual trajectories for experienced users. So here are just 4 examples where you see that people are making noisy improvements in terms of their ELO ratings with experience, but overall trend upward. When we look at the population level averages split by total experience, we see a pretty consistent increase. This is the average for people who had played anywhere from 100 to 119 total games, but this trend holds for all experience levels that we looked at, suggesting that people are in fact improving the task. Okay, so to just come back to our didactic plot from earlier, these results together suggest that people in our task are somewhere maybe towards the top right corner here. So for the last portion of the talk, I want to build up a joint model of learning and dropout to sort of start to get at mathematically how this process is happening. So to do this, we started with the data, which is each user having an initial ELO rating and 20 games of gameplay experience. Then we have some decision process, which I'm going to fill in a second. But at the end of that, each user has to make a choice about whether to play another game or drop out. And of course, if they drop out, then gameplay is over. They'll have a final ELO rating and a total number of games played. So we know that this decision process should be governed by learning and dropout, where people improve at the task somehow and then decide whether to continue. But in fact, we can fill this in even a little bit more because we've just gone through some analyses that give a foundation to model each of these processes. So how does this learning plot now lead to our first model component, which is learning rates? So for that, we assume that each user has an underlying learning rate that stays constant across gameplay, and that playing a game leads to a noisy increase in ELO ratings. We saw that in the individual trajectories. We run a linear regression per user, which we already did at the average level for testing statistical significance. And that's going to give us 2 parameters that we care about in terms of learning, which are the learning rate, the increase in ELO, and some noise on that as well. For the learning rate, we draw that from a normal distribution, which has a mean and a variance that are at the weighted mean and the variance of the user slopes from the regression. And the noise is drawn also from a normal distribution with its mean at 0 and its variance at the variance of the residuals also from the linear regression. And this gives us a very nice update rule for the ELO ratings, where the rating at a certain time point is the old rating plus some learning rate plus some noise. So we can plug that in there. And we want to do the same thing for our second model component, which is looking at dropout. And luckily, the logistic regression that we already did maps pretty nicely onto this. So each user has to decide whether to stop or continue playing based on the two factors that we decided drive dropout behavior from earlier. And then we just need a stopping probability for each game. And we're just going to grab the coefficients right from the logistic regression and have a nice rule also for the stopping probability. We can plug that in as well. Okay, so now we can take this mathematical description and run it forward in order to see if it replicates any of the empirical results that we found earlier. So we'll compare the data in the model for task performance, dropout behavior, and learning trajectories. So for the task performance, you see the same correlation from earlier, just for larger windows since we ran the model just in the blocks of 20 games that we had for the EULA rating computations. Dropout behavior looks almost identical on this heat map, and the learning trajectories also follow the same general upward trend. Of course, we still want to improve the model, and sort of the things that we're working on now are thinking about the learning rate maybe being adaptable such that it decreases with experience. You do see a little evidence of a slight curve in the data for the learning trajectories. We're also thinking about additional factors that might influence dropout in learning, such as the actual physical time of interval between games and the AI opponent strength. So this is a lot of this is preliminary work that we're still working on. So I'm going to wrap up in a second. But before I do, I wanted to preview another line of ongoing work, which is centered around understanding these behaviors at a process level. So the model I outlined so far operates at this sort of higher level of decision making, and I've actually said nothing about actual human choices. So in previous work, which is the preprint that I mentioned, we have built a choice model for this task, which is a planning model. I'm not going to give a lot of details about that here, but very broadly, this uses a value function and tree search in order to capture human behavior pretty well by computing the value of states and then looking at how those states might evolve into the future. And we've taken components of that model and see how they change with experience alongside this task performance increase where people's EULA ratings improve. And the conclusion from that is that people show an increase in planning depth, which is how far they look into the future, and a decrease in feature drop rate, which is how often they overlook certain parts of the board. And these jointly contribute to a lot of the increases in playing strength. Now, of course, this also says something about what's happening during learning, maybe at a different level of abstraction than the dropout model I showed. And we eventually like to link these two models together by looking at how maybe these metrics change with dropouts or vary across our data set. But if people have ideas for any joint modeling between these, I'd be super interested to chat. Okay, so just to wrap up and summarize, we used the large-scale data to look at learning and dropout, established that playing strength and experience are correlated, that current playing strength and experience drive dropout behavior, that playing strength increases with experience and can be linked to these metrics from the planning model, and we built up a joint model of dropout and learning that replicated the data. So huge thanks to the lab, and I think we have a minute or two for questions, so I'm happy to take anything if there is.
Hi, can I ask a question?
Yes, go ahead.
Yeah, this is more of a clarification question because I have no idea like what ELO rating is about. And
Yes.
I'm wondering if you can say more because it sounds like a participant can only get an ELO rating once they are done with 20 games.
Yeah.
And it sounds like a pretty high bar. Like what happened to participants who drop out before like 20 blocks? So does that kind of imply that some kind of, I don't know, like trajectories of that dropout curve is not being captured in the current data set?
Yeah, so it's a really good question. So it's not that we can't calculate ELO ratings for people with less than 20 games. We certainly can. It's just that we need a relatively decent sample of games to see how people comparatively play against the AI agents. And so we wouldn't really trust ELO ratings for someone that had maybe only played a game. It's not necessarily a good measure. So if we wanted to look at dropout behavior or learning behavior, anything like that, for people who had played relatively few games, we need to do something else. And we might want to do that by looking at people's win-loss ratio or other things like that. So we certainly can do that. Does that help?
Yeah,
Okay.
Thank you.
Any other questions? If not, we'll...
I guess this is less than a question, but a weird analogy that occurred to me. That is, what you were talking about here is strangely reminiscent of decisions to stop recalling when you're recalling a category or a list. And we used to explore the question, why do you stop? And just to give an example of a similar result, we thought maybe a succession of failures to recall would be a good stopping rule, but that didn't work very well. We found that total failures was a better account and so on. So it's sort of a weird analogy between stopping and learning in these games and stopping recall when you try to recall.
Yeah, no, thank you for that. And I think there are a lot of, this is not the first field that has looked at, when people stop. And I don't know that literature specifically, but it would be interesting to sort of look at how those findings relate. Wade and I have had a lot of previous conversations about kind of disparate fields that touch on similar things. Like another example, survival analysis, which really looks at when people continue surviving with the task or not, and that's applied also mathematically as a tool to a lot of other fields. So I think there are a lot of related sort of literatures we can draw from. Okay, so I think we'll move on. So our next talk